Hello, everybody, and welcome back. Today, we are here to attend a webinar on SoC functional verification on NXP Campus Connect. For the benefit of the people who could not attend this session personally, we would be recording this session. So, Rahul, you can start the recording now. So, today we have an esteemed panel of verification experts from NXP. We have Ravinder Pal Singh Dhanjal, we have Parag Joshi and Madhusudan. Ravinder has been associated with NXP for more than 23 years now. Parag is based out of Bangalore, and he has an overall experience of 17 years. Madhusudan is based out of Pune, and he has also overall experience of more than 15 years. So I welcome all of you on this forum, and Ravinder, you can start the presentation now.
Okay. So hello everyone. So first off, let me welcome you. Very warm welcome to everybody for this session of NXP Campus Connect. So in this session, my colleagues and I are going to describe SoC functional verification, which is just one of the steps that are involved, one of the many steps that are involved in SoC design flow. Okay, so it is a fairly basic, we have kept things at a fairly basic level, so it's easy to understand. For some of you, it'll be new knowledge that you will take away from this session. And also for some of the advanced students, maybe masters and beyond, they may already have knowledge on some of the concepts that we have covered. So in that case, it will serve as a refresher, simply as a refresher for them. Okay. So let me take a moment to, yeah, one second. Yeah. So introduce my colleagues, just one-liner on each. So Madhusudan is working in our Bangalore office, and he's working on radar frequency processing SoCs verification. And Parag Joshi is part of our team, verification team in Pune, and they are working on Wi-Fi SoCs. And I have worked on SoCs which are in computer networking domain and cellular baseband domains earlier. Okay, and currently I'm working for the verification team in Noida. All right, so this presentation is structured in 3 sections. So in section 1, I will make an introduction to verification, all the basics around it. And in section 2, my colleague Madhusudan will take you through more of the process and flows that are involved and how things are done in verification. And then finally, Parag will take you through section 3, which will talk about techniques and tools that are involved and currently used in the industry for verifying the SoCs. Okay, and in case you have any questions, you can note down the slide number, which is at the right side bottom, and you can note down your questions and post this presentation, and there will be a Q&A section where you can ask those questions, and we'll try our best to answer those. All right, so introduction to verification. Okay, so imagine, this person, there's a person shown here who's nicely sleeping, but he has bought a clock, an alarm clock from the market, and he wants to put an alarm on that. He has put an alarm for 6 a.m. In the morning, and he sees that the alarm really functions well on Monday. It goes off at 6 a.m. So he's happy. On Tuesday, it doesn't really function. On Wednesday, Thursday, it goes well. And on Friday, again, the alarm doesn't go off. So he's kind of irritated on why this is happening on some days correctly and why not on others. So he contacts, to the manufacturer and says, this is happening. And manufacturer of this clock debugs and tells him that, oh, there's a problem in one of the ICs that we have used in this clock, and the problem is that if you set the minute of the alarm to 00, the alarm will not work properly. So you have to set it at so workaround. You have to use you set it at 5:59 or 6:01 a.m. and then it should work for you. So this guy is still irritated. He invested in this clock, and but it doesn't work properly. But he's okay because he's got a workaround for that. Now consider another example. This person, he has got a pacemaker, which is also a part of it has electronics in it, and the function is that the electronics generates a periodic pulse to the heart of the person, different areas of the heart of the person, so that the rhythm the heart can beat correctly. If the person is suffering from arrhythmia or some of those kind of problems. Now imagine, if there is a bug or there's a problem in this artificial cardiac pacemaker. So obviously, this person will not have the patience and the time to, go find out what's gone wrong with his pacemaker and then get a workaround and all that. He'll be dead by that time, right? So if you see the impact of a functional failure of electronics, things can be really, it can range from causing irritation to somebody to even causing a fatal. It can be fatal for somebody depending upon the application. Okay, so one of so these problems. So one of the reasons why these problems or the electronics can fail is due to bugs, presence of bugs. And this slide shows a typical development cycle of a product. So we have the development phase. To the left, you can see the development phase. Just turn on the pointer. Yeah. So development phase, during which the product team actually develops the product, and then it is taped out somewhere here and goes, and then hardware is received. It goes into validation phase, where it's validated that it's functioning correctly, and then it goes into the end user products, which the end user uses. Now, what is the cost of finding the bugs and fixing them at different points? So obviously, if you find them in development, things are still soft. They are on the computer. They're in the soft form, in form of files. You can still rework, and fix the problem. And at most, what will happen is there will be scheduled delays in the program. And that is the cost you're paying, right? At most, scheduled delays. But now consider that bug escapes this development process and is actually caught in validation phase. So here you have additional cost, because it's very difficult to debug a piece of silicon because the tool's capability is limited and you do not have visibility into the chip. And if you find a fatal bug here, then you have to refabricate the chip. And of course, there is a huge mass cost involved. So it's getting costlier now. Now, if you move to end user experience, as we have seen before, if there are bugs that escape to the end user, and so here, there will be a huge cost involved, because then the product will have to be recalled, and then maybe potentially they have to be replaced, and also there is credibility loss, right, for the company. So the cost again adds up. So if you see at the bottom, the cost of finding and fixing bugs is low to the left, and higher, and goes on higher as we go to the right. So it is always desirable to find bugs as early in the life cycle as possible. Okay, so what is the role of functional verification then? So verification is actually done in development portion of the product life cycle. And of course, verification means that you have to actually check that your product meets the specification, and ensure that all the bugs are actually found during the development phase and not during the later phases of validation and even customers end. So that is the goal of verification. Now, this problem is easy to talk about, but it's not really a simple problem, because on the right is showing a typical automotive radar microprocessor, where you have a lot of IPs integrated on a typical SoC, right? In today's SoC, you have cores, you have radar processing accelerators in this case, you have all the IPs, all different IPs. So modern complex are by any standards very, modern SoCs are very complex. Why? Because there are tens of IP designs stitched together, and there are several processor cores, so it's a multi-core system. And thousands of connections throughout the chip, because you anyway have to connect up all this, hook up all these IPs together in order for them to work together. And also there are both kinds of components, right? Digital and analog component, and several kinds of clocks and bus protocols connecting all of this together. So verifying this is a mammoth task. Okay, so what is verification? Very briefly, this slide draws an analogy with software. So in the software world, I think this is an example of C, which most people will be familiar with. So let's say the software under test. So let's say this is your software which you are actually creating, and it's supposed to add two integers. So you would have this code in C, and in order to test it, you would have a main function, you would actually call the software under test, and then you would have some kind of arrangement to supply in numbers and see what the results are. Okay, and that way, if you see here, there is a bug right there. Instead of adding, it's a multiplication. So two numbers are getting multiplied instead of addition. So if you do this properly, you will catch this bug right in the development phase. So what happens in hardware world? You have the design, which is design under test now. The language used here is Verilog. So it's an RTL model for a 3-bit counter. And in order to test this counter, you would again build a test bench around it, and call the counter inside the test bench, and do what is called verification, which is corresponding to testing in the software world. So that's it. In hardware world, we call it verification. In software world, it is testing. All right. So you may ask, if it's similar, then what is the difference in the hardware world? So in the hardware world, actually things are in hardware. That means the RTL model will be synthesized will be mapped into hardware, which is this thing is showing logic components, and it will also be laid out, by the layout tools into transistors, and then finally it will be manufactured into a silicon die. So it's actually software getting converted into hardware, and because of that, there can be several problems. So sometimes synthesis will have problem, and most of the time it is due to the way RTL is coded, guidelines are not getting followed, or maybe some tool issues also possible there. In this synthesis, there may be some problem, and the RTL model may not get synthesized correctly. So this is one source of problem that can come in a hardware world. Secondly, when we are mapping to actual hardware, we know that these are all wires and actual transistors, and in silicon we'll have actual resistance, inductor, capacitor, all the parasitics. And because of that, we have timing delays also in hardware, which is concept unique to hardware compared to software. And because of and then we know that when there are timing delays, we can have failures like setup violations, let's say between these flops, if the timing is not right, you can have setup violation, you can have hold violations, and these can be fatal because setup violations, we know that we can reduce the frequency of operation and still work around it, but hold violations are fatal and they must be fixed, otherwise the chip will come out dead. It will not function at all. Okay, so in hardware, thus one additional step is needed, which we call as gate level verification. So we do have to verify the timing aspects and the netlist aspects of the design also. And so we take the netlist, we have the physical layout of that design, and then we take the same test bench as we used for verification of RTL model. Then we feed it, we extract timing from the physical layout, and this is done by tools. So there are tools can extract timing, and we feed it into the test bench. And we feed our gate level netlist into the same test bench. And then we simulate it with timing. So in effect, what we are doing is we are actually verifying the gate, the hardware version of the RTL model, as well as the timing, actual timing from the layout. Okay, so with that background and that very basic primer on verification, I will hand it over to Madhusudan, who can take you through more details around how verification is implemented and how it fits into the overall flow. So Divakar, can you please give control to Madhu?
Do you see my presentation, Ravinder?
Yes, we do.
Yeah. Okay. Thank you, Ravinder, for that good overview on verification. Let us now look into the aspect of process and flows and how we carry out functional verification. So let us start by looking into what functional verification is. So if you remember on one of the earlier slides, Ravinder explained how the chip we are going to design is coded using hardware description language, referred as HDL, and also referred as RTL most of the times, where RTL stands for register transfer level. In functional verification, to begin with, we are trying to make sure that the RTL code of the design is working as intended. And so the question we are trying to answer is the coded design working as we expect it to work? Keep in mind that the functional verification environment that we create around the design that we are trying to test is also created using hardware description languages. Now, is the functional verification the only testing method that we employ on an integrated circuit? No, actually there are two more major testing that we do that will ensure that the chip that we are eventually going to create will work as intended. The second one is called the DFT verification. Here the question we are trying to ask is, can we test the manufactured IC if it is not found to be working? So let us take an example to talk in more detail on this one. Let us say a team creates the RTL code for the intended IC and functionally verifies the coded design and finds that it is working fine, then tapes out the chip and gets the physical IC in hand. When they put it on board and start to test it, let us say that the chip does not function. Any debug that needs to be carried out on the physical IC needs to be done using its primary input and output pads, unlike in functional verification where we can probe everything inside the design and plot the signals on the waveform. This is not possible in on an actual chip, since we are dealing with a fabricated IC. In order for the team to look inside the chip to figure out what is going wrong, that is making the chip not function, certain logic needs to be added inside the chip logic for testing the chip. This additional logic that is added is called design for test, or DFT. Once logic that is needed for testing the chip is inserted by certain DFT tools, verification needs to be carried out to ensure that we indeed can test the chip if something goes wrong, and this is called the DFT verification. Now finally, the third major testing method is validation. Here the question we are trying to answer is the manufactured IC working as intended? Here the physical manufactured IC is put on the board and it is taken through the same kind of testing that was done during functional verification to ensure that the physical IC is working as we intended it to work. Just keep in mind that these are not the only three methods. There are more methodologies involved. At a broader level, these form the three major methods that we employed for testing on an integrated circuit. And today's focus is going to be on functional verification. So in the ASIC design flow, where does the functional verification fit in? So you can notice that we usually start the ASIC design flow with design specification followed by behavioral description. Once these are ready, we start to translate the data we have from behavioral description to RTL using hardware description language. Then we carry out functional verification like explained earlier on the RTL version of the design. So we do one level of verification here. Functional verification is also carried out on gate netlist, which is written out by the synthesis tool by reading RTL version of the design. So for instance, the RTL is taken by a tool which can synthesize it and convert it into a gate level equivalent. Then at this point, we are still doing functional verification on the synthesis, or what we call the scan netlist, and it is also referred to as pre-layout gate simulation, the functional verification that we carry out here. The synthesized netlist is also called scan netlist because it contains certain DFT related scan structures as well when synthesized. The synthesized netlist then goes through a process of floor planning and place and route, after which the layout netlist is available. At this stage, the net and component delays are also available from the tools in a standard delay format, also referred to as SDF, using which the layout netlist simulations can be performed with timing information as well. At this stage as well, we are carrying out functional verification. So if you see, functional verification is carried out on RTL, it is carried out on pre-layout netlist, it is carried out on post-layout netlist, and when you do post-layout netlist simulations, you also ensure that your timing is also taken into effect for simulation purposes. So it must be noted that the same set of tests or reduced number of tests which are created for RTL are used when we carry out the gate level simulations, either at the pre-layout level or the post-layout level. So this is where the functional verification fits into the ASIC design flow. Now let us look at the process involved in verification. So we start with the functional specification of the design, from which we create a verification plan. A verification plan will capture in detail the kind of tests that are needed to ensure that the design works as planned. Once the plan is in place, we build the test bench and test cases and all other things that help us in verification, like for instance assertions, coverage definitions, etc. Then we take the test bench and test cases through a process called regression to ensure that all the test cases that we have created are simulated and are found to be passing. The regression is also run at least mandatorily on the layout netlist and not just on RTL, and it is done at a stage when the layout netlist and the timing information in SDF format is available here. Then we analyze the functional code coverage data, and if the data is impressive, we move on and consider it to be a sign-off stage, and we say that the verification process is complete. Otherwise, we repeat the whole process till we are done. Certain details like coverage and methods of verification like formal are all explained later in the next section by my colleague Parag. One of the methods of capturing the verification plan that I spoke about in the earlier slide is shown here. So this is a screenshot of a verification plan for a UART design captured using a tool from Cadence called vPlanner. You can see on the right hand side the parts of the spec that is imported is highlighted, and equivalent test points are captured on the left hand side. The tool can also annotate data from regression to let us know how many test points are covered through simulation regressions. So let us say you have identified 10 test points here, but your simulation regression has only 5 passing test cases. Then you can figure out that 5 out of 10 test points are still to be done, and you have to put some effort in getting them to the completion stage. This is one of the good methods, as it can give you an indication if every part of your design is covered by a test point in functional verification. Keep in mind that this is just one of the methods. There are several methods and several tools available, of which you may choose just one of them. The method of capturing a verification plan could even be as simple as an Excel sheet where you mention the section number in the specification for every test point that you capture. So a design nowadays is an integration of several IP blocks. So when I say IP blocks, it is it is somewhat like an I2C or an SPA or UART block or USB kind of an IP. When the design is big, it is beneficial to break down the task of verification for ease of management. So this is needed to be done, because if you take everything and do it in one phase or one stage, it's going to be difficult. It's like our West Bengal elections. You have to do it in several phases because the state is big and you have to handle a lot of complexities. So this is the reason a hierarchical verification approach is chosen. You break down the task of verification into several parts. So let us take an example design and then talk in detail. So let's say, for instance, that we have a design with a few processors, protocol translation bridges, and certain peripherals like UART, GPIO, USB host, PCIe host, etc. What I'm going to talk now is at what level of the design we are trying to verify the functionality. One of the levels of verification we do is called the module level verification. In the example design, for instance, we just pick one of the smallest complete component like UART and verify it independently of other components in this design. Meaning, we take the UART block, rig up a test bench only around it, write tests to ensure that the UART can transmit, receive at various baud rates and all that, and then we ensure that the UART works as intended. The intention here is to ensure that all functions and interfaces of the IP are thoroughly verified. Next, we have the subsystem level verification. So if you see the orange circle around here, now in a subsystem level verification, the intention is to verify that the interconnection of several IP blocks are done properly and they are able to communicate with each other. So for instance, here, if we take this subsystem with a AHB bridge, and then on the other side of the AHB you have several peripherals connected, our aim is to make sure that these are connected properly and they are working as we intend them to work. And also, it is to be noted that when we are doing subsystem level verification, we assume that all the IPs have been module level verified earlier. So like we spoke about UART, we expect the USB host or the PCIe host, everything to have been pre-verified at module level, and only the interconnection of these IPs in this subsystem we are trying to verify. So the term sub in a subsystem is used to indicate that the subsystem will end up getting used in a system eventually. So that is one of the things that is a necessity. And then like this subsystem that I spoke about, you could have another subsystem like shown here. You could have a third subsystem probably which encompasses this much of your design, and it all depends on how you break down your design for lower levels of verification. So you can have any subsystem in any way you wish, and it should just be done in such a way that it works for you. The final level of verification is at the SoC level, SoC being the abbreviation for system on chip. So you have the system level verification or the system on chip. System on chips or the SoCs will have at least one processor and a few memories that go along with it. And it is a system, meaning a full system for a particular design specification. In SoC level verification, we ensure that multiple subsystems are connected properly and they communicate as we intend them to. And it should be noted that splitting a design into subsystem is actually not mandatory. If the design complexity is small, then you can as well after module level verification, you can as well do an SoC level verification. So sometimes the intent of SoC level verification will be similar to that of a subsystem verification, which is to ensure that all IP blocks are connected properly and then communicate as intended if SoC does not contain a subsystem. With the complexity of designs increasing as time passes, it is important to choose a methodology of functional verification that gives us an advantage towards time to market. There used to be an era where the test cases created were all directed in nature. This would take a long time in reaching the verification completion stage. With the advent of constraint random methodology, the test cases randomize the scenarios with the meaningful constraints, which results in achieving the same amount of verification much earlier, resulting in the productivity gain that is shown on this picture. So you are able to achieve the same amount of requirement in a much earlier time. Taking an example, if you are verifying, let's say, a UART design, you do not need to create directed tests where one test tests the transmission with the different transmission lengths, another reception with different lengths, a third one with different baud rates, etc. With constraint random methodology, you can just have one test if you want it that way, of course, which tests transmission, reception at different lengths and different baud rates, etc. with back-to-back transfers. This allows us to reach the coverage goals also earlier in time. So you can gain quite a lot of quality and time with constraint random verification methodology. Now let's look at something called as low power simulations. In today's world, we have more and more devices that need to consume as less power as possible, as these devices need to run on battery power. There are several methods to achieve reduced power consumption. One of the methods is to divide the design into several power domains. There will be one always on domain and several domains which can be switched on or off, which can be controlled from a logic in an always on domain. So with this method, you ensure to turn off parts of the chip that are not needed at a particular point in time based on your requirement. So one of the examples that we can talk about is our mobile phone that we use on an everyday basis. When your mobile is in your pocket or in your bag, you only need the networks and the related circuitry to be active, and the display can be off. With display being one of the portions of a mobile which consumes more power, and it is now being switched off, the mobile is able to run off the battery for a longer time. So in the picture on this slide, you can see it is showcased how we have split a design into three power domains. So we have always on domain, a domain A and a domain B, and the signals are exchanged between these power domains. It is possible that different power domains can be operating at different voltages, which also helps in reducing the overall power consumed. So for instance, a portion of your chip is able to work at a lower voltage. That's actually good to reduce the overall power consumption of the chip. So in this, you can see that this portion of the chip works at 1.8 volts, whereas this portion of the chip works at 1.2 volts, and the always on is at 1.2 volts. Structures such as level shifters are inserted when a signal goes from one domain operating at one voltage to another operating at another voltage. Structures called isolation cells are inserted in the path of a signal which is crossing a domain. These structures, which are usually inserted during synthesis, ensure that when a domain is switched off, the signals going from switched off domain to the domain which is on does not end up corrupting the behavior in the on domain due to X propagation. So that is one of the main intentions of keeping isolation cells, so that you don't end up correcting the other domain here. And CPF and UPF are actually two of the file formats that are available nowadays, in which design low power intent is captured, and these files are provided to synthesis and simulation tools to handle the power intent related logic insertion and simulation. Now let's look at a little about analog blocks. So integrated circuits don't just have digital logic nowadays, but they also have analog, like for instance an analog to digital converter, digital to analog converter, low dropout regulator, etc. So these analog portions of the design are module level verified using analog centric simulators, and the final implementation in case of analog block from the analog team is actually called as SPICE netlist, which can be used for simulations like the gate netlist in case of digital. So in case of analog simulators, the entire system matrix is solved at every time step where time is continuous. So Cadence Virtuoso is one of the examples of an analog centric simulator. Digital simulators, on the other hand, for them time is not continuous, it is discrete. So events are triggered at discrete intervals, and these events are evaluated at a distance from each other, unlike an analog simulator. So Cadence Exilium, for instance, is an example of a digital simulator. And ideally, like I said here, SPICE netlist is the final implementation of analog block, and so that should be integrated and verified at top level when we do the overall SoC level verification. When we integrate these SPICE netlists that are provided by the analog team, which are the most accurate representation of analog blocks, and carry out simulations, the simulations are usually found to be very slow. The reason is that the evaluation of analog matrix for SPICE netlists have to be done at every time step, which increases the simulator load. So this is a scenario where we want to use something for a purpose, but there is a disadvantage in using it. So what do you do in such a case? So the closest and the best analogy I could think of is in movie making. So for instance, you want to use the hero for some extreme stunt scenes, but your movie making will be ruined if the hero were to hurt himself during the stunt. So what do you do? Replace the hero with a stuntman. That is exactly what we do in analog mixed signal simulations as well. So we use an analog model instead of the actual SPICE netlist, which gives us the advantage of faster simulations. So even though we use analog models initially, just before tape out, we make sure that some important tests are run with SPICE netlists to ensure that the actual analog implementation is tested with the digital, even though the simulators are slower. For modeling, we have a host of languages that can be used. So in the picture here, you can see that as you move towards the right, the speed of simulation increases. So if you use SPICE netlist, your simulation will be slower compared to FastSPICE or Verilog AMS or real number modeling or digital, with the digital being the fastest, pure digital being the fastest for simulations. On y-axis, we have depicted how the accuracy changes. So as you move from bottom to top, the accuracy increases. So for instance, your SPICE is the most accurate and your pure digital is the least accurate. It is actually best not to use pure digital because they are not at all accurate, although they give you a good advantage in speed of simulations. So just to give an example as to why we can't use it, so let's say you are dealing with analog to digital converter or digital to analog converter. Just think, how can you model your analog portion of an analog to digital converter using just 0 and 1? It is not so possible. So it's best not to go for pure digital. So till recently, and even nowadays, the trend is to go with a language called Verilog AMS for modeling. But of late, we are seeing a real number modeling approach picking up and gaining adoption pace, and it is seen as the future trend towards modeling of analog blocks. Just for illustration purposes, here is a snapshot which showcases the same circuit modeled using Verilog, Verilog AMS, Verilog A, and also real number modeling with its SPICE equivalent. You can see that each language has its own flavor of constructs that aids in modeling of analog blocks. Now let us look at the need and advantages of gate netlist simulations. The RTL form of the design gets translated first into scan netlist through the process of synthesis, and then the layout netlist through the process of place and route. The layout netlist is closer to reality and also gives us the capability to run simulations with actual net and component delays in the component delays for the nets and components present in the netlist, and that we can do using the SDF file. So it is important that we verify the transformed version of the design as well, at least mandatorily the layout netlist, and run simulations with SDF to make sure that there were no issues during synthesis or place and route. Sometimes when the RTL code is synthesized, the synthesis tool can convert certain logic visualized one way in RTL incorrectly to gate level equivalent. You can see that when what we intended in RTL was like the picture on the left, but what was intended was like the picture on the right. Sorry, what was inferred was like the picture on the right, and with an AND gate at the output of the flop, it can cause glitches. And sometimes the tool also can optimize certain logic in a way that was not anticipated. Like in this picture, now this resultant circuit here can cause glitches. So these kind of incorrect inferences and optimizations can cause glitches at certain places in the design, which can also result in circuit not working as we have envisioned in the RTL code. So gate netlist simulations help in catching such issues. And glitch related issues are not the only kind we can catch during gate simulations. Rather than just talk on the kind of issues you can catch, let me show you what issue we caught during gate level simulations in one of our chips, and how we will take you through a real life example. So we noticed a timing violation with a particular test, and the timing violation stated that there was a setup violation on a particular flop. The flop path is shown here, and in the waveform, due to the timing violation, the flop output was going X, which was propagating towards further circuitry, and that is what led to the test failure. So you can see the output of the flop is going X intermittently once in a while here. Then the circuit leading to the flop having the timing violation was analyzed. So all the signals from the queue of the previous flop, which was responsible for providing data to the failing flop, till the D input of the violating flop were plotted. So on the waveform, you can see that we noted the time delays that were as seen in static timing analysis. report in blue boxes, and the delays as seen during simulations in yellow boxes. So we noticed that one of the time delays seen in simulation was quite large, 402 nanosecond compared to static timing analysis reports 255 nanoseconds. So this was quite a huge difference. So when discussions were held due to figure out why there was a huge difference, it was figured out that the path in question did not have a synthesis constraint. So in summary, netlist simulations are important as they help you catch issues related to glitches and also those which cannot be caught with just help of static timing analysis tool. So that gets me to the end of my part of presentation. Next, Parag will walk you through the techniques and tools.
Yeah, sure. Okay, let me share. Is my screen visible?
Yes.
Okay, thanks. Okay, so thanks Madhu for sharing the process and flows for use for the verification. So in this technique, I'm going to basically in this section, I'm going to show you the techniques and tools that are used for verifying the design. So there are major three types of functional verifications. So one is the dynamic simulation. The second one is static verification. We also call that as a formal verification. And then last is hardware emulation. So in the subsequent slides, we'll probably go in somewhat details, not full detail, but somewhat details of each of these types. So starting with the dynamic simulation. Yeah, the purpose of the dynamic simulation is to verify the individual IP, or it could be multiple IPs inside SoC. So SoC could have tens of IPs, and you might want to verify the interconnection between those IPs. So functional simulation can be used for that. Dynamic simulation can be used for that. It is also basically used to verify the SoC, different IP connectivity, and end-to-end checking. Dynamic simulation also can be used to verify functional behavior of the design. So in this diagram, what we are going to show you is basically this blue highlighted box is a design under test, which we are going to verify. And to verify that design under test, we need to create certain verification components like stimulus generator, which is going to generate the stimulus to the DOT. And based on that stimulus, DOT is going to generate the output. Those output will be captured in the checker or predictor module. There could be another components like coverage collector to indicate how much we are covered with respect to the design code. So this is in general the simulation setup. Going on to the next slide, basically, what is the flow for a dynamic simulation? So in this case, we are trying to create the test bench first. So creating the test bench, I'll go back to previous slide. Creating test bench is basically creating these different components like stimulus generator, checker or predictor, coverage collector, and there could be many more such components depending on the design specification and then complexity of the design. So first step is basically to create the test bench. The second step is basically we are going to instantiate the DUT, which is design under test, which we are going to verify inside the test bench. Then we provide the stimulus. We compile the design in the test bench, compile design and the test bench. We are going to run the simulations. We are going to run the simulations in the sense we are Now we are going to actually drive the inputs of the DUT and making sure the outputs are getting toggled in the specified way. Then we observe the output with the help of checker module or predictor module, and then finally in uh, the check phase, we are going to check the correctness of the design output. So this is the flow for the dynamic simulation. In this slide, I just basically copy pasted one of our design signals. So this design could be any design. What you need to do is you just need to run the simulation with specified options to enable the waveforms. Those waveforms can be loaded into the simulator, and each and every signal inside the design, also probably to some extent inside the verification, can be loaded into the simulator window, and you can check the expected behavior of that. So in this simulator, this is simple FIFO, where data in is the input to the design. Clock and reset, of course, are the input to that design. Write enable and read enable are again two inputs. Those indicate that when read enable is asserted high, you're going to read from the design under test. So in this diagram, we can say that at this particular time, the read enable signal is asserted high. That means we are going to read from the design. So design is going to give you the output, data out, and we can see that data output is getting toggled. We can see basically the correctness of the each and every signal using this waveform viewing technique. Apart from this input output, we could even load the internal signals of the design, like write pointer, read pointers, and all those things. So in the early phase of the verification, where design is not yet mature, the verification components are not yet mature. So this basically eyeballing the each and every signal of the design and verification is very useful in debugging the basically bugs. And now when the design matures, as long as our DV matures, then we basically go with the automated way of checking the design and hunting the bugs with a checker and predictor module. So in this slide, I'm going to talk about what are the different tools, languages, and methodologies that are used for verifying the design using dynamic simulation. So most oftenly, VCs from Synopsys, Questa from Mentor Graphics or now Siemens, and Incisive from Cadence. That are the different tools that we use for verifying the design. In terms of language, System Verilog is the key language used for verification apart from Verilog. So nowadays, in general, System Verilog is the standard practice of using using that language in the verification rather than Verilog language, because it comes with some key advantages as it is based on the object-oriented programming concepts like inheritance and polymorphism. This concept can be used basically to reuse the components at different level, IP, subsystem level, SoC level, also across the different projects. So System Verilog is actually HVL based hardware description language. So that is always used in the verification. UVM is another standard, industry standard that we use for the verification, and this is a methodology. It is based on the System Verilog. So universal verification methodology is the industry-wide accepted thing for using the for verifying the design. Advantages of the dynamic simulation, it is very high in terms of visibility of the design. We have seen that you can load each and every signal in the design, and you can backtrace it, who is the driver for that. You can check the multiple, whether those are getting driven with multiple driver. You can trace back to check the X propagation and all those things. In line with that, it has got very less debug time, as a tool comes with the interactive window. You can load the design and waveform inside the window and make sure that you basically trace the issue. The third topmost advantage is that all corner cases can be verified using dynamic simulation, provided that you have uh, a mature random stimulus generator, which can able to generate all the possible random cases, valid random cases as per the specification mentioned by the design. So bugs can be identified easily with the self-checker. As I said, once the design matures and then DV matures, you're no longer going to eyeball each and every signal inside design. So basically self-checking mechanism, the predictor or checker, will automatically throw an error when it sees a violation in spec. So you just run the test case, you grep for the error, and you can just report the design team. Low cost is the last advantage for dynamic simulation. Yeah, of course, we need to pay the license fee that for the tool which we are using from the vendor. It could be Synopsys, it could be Mentor Graphics or Cadence, but this low cost is basically as compared to the hardware emulation or hardware acceleration setup that we are going to talk in next few slides. What are the limitations for dynamic simulation? So yeah, dynamic simulation in general is very low in speed. If you want to run any particular test at SoC level for, let's say, maybe for 10 microsecond, 10 millisecond, it can take up to hours. So that is one of the major limitations of the dynamic simulation. The other thing which we cannot verify with dynamic simulation, functional simulation, is timing issues like setup time or hold time cannot be verified using a dynamic simulation approach. Of course, as Madhu indicated, we need to run special gate level simulation to capture those issues. But when it comes to the functional level dynamic simulation, we cannot catch those issues. And then a simulation environment creation can be time consuming when it comes to the complex SoCs or even complex IPs, especially when the design supports a proprietary interface, a non-standard interface. Then probably we need to create all those components like a driver, stimulus generator, predictor, self-checker. So that can take some time. So this is all about the dynamic simulation. Going to the second type for verifying the uh, design with functional verification is static verification. It is also called as formal verification. So purpose of this static verification is to reduce the verification effort at the RTL level. How that can be helpful to reduce the verification effort at RTL level will basically come come to that in subsequent slide. So regarding setup and process, basically you'll see that static verification or formal verification, it comes inherently with the basically tool, and that tool uses mathematical approach to verify the design based on the property or assumption as per the specification. So in general, the setup for setting up the formal verification techniques, what you need to do is one of the input to that is your design, and other input to that is basically the system verilog assertions or assumption. And what are the assumptions? So for example, let's take in a simple example where uh, design is taking one of the input as a request, and based on that request it is going to generate the output ACK after 2 clock cycle. So you need to write this property and supply it to the formal tool, and formal tool will apply all the mathematical calculations and techniques to prove or disprove that property. So unlike dynamic simulation where we need to create or we need to write the test cases, we need to generate the stimulus, in formal, internally those scenarios will be generated, and then tool will basically prove or disprove those property whatever you supplied. Yeah, I'll basically switch the gears and talk about code coverage and functional coverage. Basically, that will be helpful in the next slide to understand. So in general, there are two types of coverages. One is code coverage and other is functional coverage. What code coverage really means is it is basically design coverage. How much RTL code that is written by the designer uh, is covered by your test cases or test benches. And functional coverage, in opposed to that, it is nothing to do with how much RTL code we have written, but what it will cover is how much specification are being covered using basic our test benches. So code coverage, it measures how well HTL or design code has been exercised by the test bench. It verifies the completeness of the verification, hitting the blocks, expression, ports, and state. So these are different terms used in verification techniques. Basically, if you write an if-else statement that is considered, or for statement that is considered as a block, continuous assign statement are the expression in the design. Input outputs are basically ports in the design, and then design will definitely have some state machine, so that is called as state machine coverage. So you are going to make sure that you possibly cover all the blocks inside the design. You cover each and every expression with all possible uh, combinations. All the ports, input and outputs are getting covered, and then state machines, all the states are getting covered. So this is again, whatever written inside the design, we are going to measure how much we are going to cover it. And this is simulator inbuilt feature, in the sense you just need to turn on the corresponding switch to display the coverage. You run single test case or multiple test case like regression, and tool will generate a report out of that, and it will basically display what the things that have been covered and what the things that are not covered or basically left out by your test case or test bench. As opposed to this, functional coverage is basically, it measures how well the functionality of the design has been covered with respect to specification. So it verifies the completeness of the verification, hitting the identified specification topics. It has nothing to do with the HDL coding. It is everything to do with the specification. So what it means, for example, design has uh, design has to be implemented using 10 different features that are listed in the document, but somehow designer have implemented only 9 features and 1 feature got left out, not implemented for any reason. then code coverage is not going to cache that issue, but functional coverage will cache that issue. So yeah, the last point is this is not basically simulator inbuilt feature. You need to write the coverage point as per the specification document. You need to create all the combinations of those coverage point mentioned in the specification, and then include that file into the simulation. And after running the single test or regression, it will give you the numbers that how much specification we have been covered and how much are left out. So coming back to the static verification is mainly used for two things. One is unreachability flow in the design. So what it really means is there is some code that is dead code in the design, and that cannot be reached or exercised even if you uh, uh, randomize all possible corners. Even then it cannot be reached. So simple example, assume that a design has a statement that if A and B both are 1, then you are going to assign C to D. So D will get assigned to C. But if by nature, if B is always 0, then that particular statement of D getting assigned to C is not going to execute at any time. So formal tool will apply again the mathematical technique, and then it is going to show you what are the conditions in the design that cannot be exercised, and we can take that particular code, we can waive it off by talking to designer, and we can focus on the remaining code. Another thing that we want to verify the design using static verification is the uh, uh, connectivity. So as Madhu and uh, Ravinder mentioned that there will be tens of IPs, they are talking to each other in all possible directions, and we need to make sure that the connectivity of each IP is correct. So recently, the formal verification techniques is very commonly used to test the connectivity, in the sense that it take design as one of the input and XML as the another input. You just probably need to provide the output of one IP and then input of the other IP, and again it will basically generate the stimulus internally and make sure that the connectivity is proper. So coming to the tools, languages, and methodology that are used in verifying the design with formal way. So Jasper Gold from the Cadence is very commonly used tool to verify that. We see formal from Synopsys and Questa, formal from Mentor Graphics or now Siemens, that are also commonly used tools. Of course, the tool won't do everything for you. You need to provide the system Verilog assertions or assumptions. That is another input to the tool, and tool will basically take that as input, and as I said, it will prove or disprove those assumptions or assertions. Coming to the advantages, yeah, it detects the bugs early in the design. So sometime dynamic simulation, as we discussed, for complex SoCs or with proprietary interface, creating the test bench component like the stimulus generator, a self-checker, predictor, all those things probably can take some time. However, you can simply write some of the assumptions as per the specification and then supply it to tool, and it can catch the bugs early in the early phase of the design. Another advantages of this formal tool is it is faster and also reliable. Uh, This also, since it is basically tool generated scenarios and it is based on the strong mathematical technique, it is quite exhaustive in the nature. Only one basically limitation of this formal tool is when it comes to the complexity, is if complexity is involved into the design with some non-standard interfaces and all those things with multiple IPs talking to each other in non-standard interfaces, then yeah, probably tool will have some limitations. So this is about formal way of verifying the design. Third and last technique is hardware emulation, or this is oftenly called as hardware acceleration. So what we are going to do in this hardware emulation or acceleration is like we are trying to imitate the behavior of the hardware described language RTL with another piece of RTL. So what it means is basically we'll go through the flow. RTL source code is available over here. This is nothing but the design code. It will go through the process of compilation, then synthesis. We'll partition the design because that design may be large. It cannot fit in single hardware like single FPGA. So we need to partition that and then we need to make sure that the design implementation is complete, and then we are going to basically put it on the uh, FPGA or Palladium. So we need to provide some configuration files so that it basically runs on the another hardware. So purpose of this emulation, hardware emulation technique is to find the issues at the system level with the live data. So many times at SoC level, it is very complex to run the simulation because slow nature of that. As I said, probably if you want to run the simulation for 10 to 15 millisecond, it can take up to 3 to 4 hours depending on the size of the design and other parts, like whether you want to see the DUMs, you want to load the waveforms and all those things. So definitely it is going to uh, have some challenges when it comes to the SoC level using dynamic simulation. However, since this is basically we are imitating the behavior on the hardware itself, so it is fast and quick enough. Also, one of the major advantages of this hardware emulation or acceleration techniques, you can basically enable the software team for development of the software stack. So that is the one of the advantage of the hardware emulation. So tools, languages or methodology used in the hardware emulation. Very commonly we use Palladium. Palladium are nothing but the hardware boxes that on which we basically load the bit file of the design and we verify it. So and then Velocity from the Mentor Graphics is also common tool that we are going to use in the hardware emulation techniques. Advantages, definitely, as we just spoke, higher speed, of course, than the simulator is the major advantage of that. Parallel verification, yeah, in general, in most of the companies, these three techniques like dynamic simulation, um, static way of doing of verifying the design, and then hardware emulation technique are started in parallel. So just to make sure that we catch the bugs as early as possible with wide range. So yeah, this is the parallel verification efforts that we are going to make with hardware emulation technique. Again, in this technique, unlike the other two, static or formal way of verifying it or dynamic simulation, we cannot basically enable the software people to develop the software stack. But in this case, hardware emulation, since we are basically imitating it on the another piece of hardware, and the development of the software is possible over here. Limitations of this is, this is since this is another hardware, it is very expensive, especially the Palladium boxes or Veloce from Mentor. Those are extremely expensive. It can take a long time for initially for setting up the flow. Depending, again, it depends on the complexity of the design, SoCs and IPs inside that. And not all functional paths can be covered using hardware simulation. Assume that there are some SerDes which runs at 20 Gbps. We cannot basically run the hardware emulation using 20 Gbps on FPGA or Palladium. So we need to insert the speed bridge. We have to scale down the speed, and then only we can basically enable the hardware emulation or acceleration techniques. So not all paths can be covered in hardware emulation technique. That is one of the limitations of this. So yeah, with this, we probably are done with all the three techniques, the dynamic simulation, static way of verifying it, and then hardware emulation technique. As I said, all these things are started in parallel, but when we say, when to say actually we are done with this. So there are some criterias which we call as sign-off criterias. One of the criteria is code coverage. So we at least want to make sure that all the code that is written in the design is covered with 100%. Of course, there will be some code that cannot be reached, as we discussed previously. So those can be waived out by talking to designer, but 100% with approved waivers is one of the sign-off criteria. So this is about the code in the design. The other thing is functional coverage, where we want to make sure that design is covered in all aspects with respect to the specification. So in this case as well, we need to make sure that we get 100% of functional coverage with approved waivers from the design team. And the last one is, no known bug should be open at the time of closing the verification. We generally call that as a RTL RTL freeze phase, where we are going to freeze the design and it will be sent to the backend. So at this time, at the RTL freeze time, we don't want to left out any open issues in the design. We basically want to close it in the sense we make sure that we generate a stimulus, we verify that particular issue, and then make sure that test is passing, self-checker and predictor is not complaining, and then we close the issue. So these are the three main sign-off criterias: code coverage, functional coverage, and no bugs are open at that time. So I think with this, this was my last slide. I think we are open for questions.
Yeah, thanks. As far as there's a one question in queue, as multiple IPs used while designing are vendor agnostic, and what are the challenges faced while integrating those IPs?
Can you give more details? It's not very clear. the question?
I'm repeating the questions again. Multiple IPs used while designing are vendor agnostics. And what are the challenges faced while integrating those IPs?
Uh, okay, the vendor agnostic IPs. Actually, there's no such thing as a vendor agnostic IPs. So we have two types of IPs. One that comes from a particular vendor, the IP, that means the external company that is creating that IP. So we call it as third-party IP. For example, Synopsys may create a DDR controller. So that we call as a third-party IP, and that is from vendor Synopsys. And then there are homegrown IPs that are also used inside, for example, clock control IP or more such IPs, for example, I2C controller or other accelerators which are used. So those are created by the company itself. So those are like homegrown IPs. And so those two types of IPs are integrated. Some of the issues that can come from third party IP, usually the third party IPs or the vendor IPs, so they are not just given to one company, right? So they are being sold to many companies, and by that very fact, they go through different flows and different simulators. They are tested with different simulators, so they are pretty stable. But one of the issues that we often see with third party IPs is that uh, so NXP itself will have some kind of design flow, right? Proprietary design flow. So it's possible that the vendor may not support all of the steps of the design flow that NXP is using. So that is where we have to negotiate with the vendor and say that can you do this step also, because it is part of our quality control process. So that is where we have to negotiate with the vendors.
Okay, I hope you'll satisfied with your answer. The next question: how are the opportunities in front end VLSI?
How are the opportunities in front end VLSI? So it's not really front end or back end, because as we explained, right, the design flow has a lot of different steps. You have right from architecture and specification up till back end implementation. So it's not that you have more opportunities in any one or the other field. So whichever company is creating, SoCs, they will have opportunities in all the different fields. But in verification, if you consider only the verification part, usually it is resource intensive. A lot of people are usually needed in the verification field.
Okay, thanks, Ravinder. Next question is simulations versus emulation, and will emulation take over simulation?
It is nothing like one basically is going to take over the other. As I mentioned, these are all different techniques that are used as a parallel effort. The simulation, the formal techniques, and then emulation. But I mean, everything has its own advantages, so it is not like one is going to replace down the line with other. I hope that answers the question.
Yeah, well. Uh, if anyone any question, please raise your hand and type in chat box. Still no question, Ravinder. Please raise your hand or type in chat box if any question and doubt.
Okay, I think we are. There are no further questions. Then I think we are pretty much done. Thanks, Ravinder, Parag, and Madhusudan for an excellent presentation. And for the attendees, if you have any further questions, please let us know on LinkedIn, and I will pass across your questions to Ravinder and Parag and Madhusudan so that they can answer to the needful. Thanks a lot, and we will meet in another 2 weeks with a presentation on software or system engineering. And take care. Bye bye.
Okay, thanks. Bye bye.
Thank you. Bye.